From the dawn of humanity, we have gazed at the stars with wonder. The vastness of space has always beckoned us, igniting a desire to explore the unknown. However, the immense distances between stars and galaxies seemed insurmountable, an impossible gulf separating us from our celestial neighbours. Traditional methods of propulsion, even the most advanced rockets, are simply too slow for interstellar travel. The limitations of conventional spacecraft have fueled a universal yearning for faster-than-light travel, a dream that has captivated scientists, science fiction writers, and the human imagination for generations. This dream of exceeding the cosmic speed limit, the speed of light, is deeply embedded in our desire to explore the universe. We long to visit other star systems, to witness the birth of planets, and perhaps even to encounter other intelligent life forms. The ability to travel faster than light would not merely be a technological marvel, it would be a transformative event for humanity, opening up a universe of possibilities and fundamentally changing our understanding of our place in the cosmos. The quest for faster-than-light travel is not just about reaching distant stars. It is about expanding the boundaries of human knowledge and pushing the limits of what we believe is possible. In 1994, Mexican theoretical physicist Miguel Alcubierre proposed a radical new concept that sent ripples of excitement through the scientific community: the Alcubierre Drive. This groundbreaking idea offered a tantalizing glimpse into a future where faster-than-light travel might be possible. Alcubierre's proposal was not merely a flight of fancy, it was a rigorous mathematical solution to Einstein's field equations, the equations that govern the behavior of space and time according to the theory of general relativity. Alcubierre's solution described a mechanism by which space-time itself could be manipulated to achieve faster-than-light travel. Unlike traditional propulsion systems that push an object through space, the Alcubierre Drive envisioned a spacecraft that could essentially ride a wave in space-time, compressing the space in front of it and expanding the space behind it. This concept, though highly theoretical, offered a potential loophole in the laws of physics as we understood them, a way to circumvent the seemingly insurmountable barrier of the speed of light. The Alcubierre Drive, if realized, would not simply be a faster spaceship, it would be a fundamentally new way of traversing the cosmos. To grasp the revolutionary nature of the Alcubierre Drive, it's essential to understand that it doesn't involve traveling through space in the conventional sense. Instead, it proposes manipulating the very fabric of space-time itself. Imagine a surfer riding a wave. The surfer doesn't propel themselves through the water as much as they are carried along by the wave's energy. Similarly, the Alcubierre Drive envisions a spacecraft enclosed in a warp bubble, a region of space-time that is compressed in front of the ship and expanded behind it. This distortion of space-time would, theoretically, allow the spacecraft to ride the wave, effectively moving faster than light without violating any physical laws within its local frame of reference. The ship itself wouldn't move faster than light within the bubble. Rather, the bubble itself, carrying the ship along with it, would move through the fabric of space-time. This concept, though mind-boggling, is grounded in the principles of Einstein's general relativity, which describes gravity as the curvature of space-time caused by mass and energy. The Alcubierre Drive takes this concept a step further, suggesting that we might be able to artificially manipulate this curvature to achieve faster-than-light travel. The Alcubierre Drive, though a product of 20th century physics, has its roots firmly planted in the groundbreaking work of Albert Einstein. Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity. It posited that gravity is not a force acting at a distance, as Newton had proposed, but rather a consequence of the curvature of space-time. Massive objects, according to Einstein, warp the fabric of space-time around them, much like a bowling ball placed on a trampoline would cause the fabric to sag. This curvature of space-time is what we experience as gravity. The Alcubierre Drive cleverly exploits this principle of space-time curvature. Just as a massive object creates a gravity well around it, the Alcubierre Drive proposes creating a similar, albeit highly controlled, distortion of space-time using a hypothetical form of energy. This distortion would compress space in front of the spacecraft and expand it behind, effectively creating a wave that the spacecraft could ride. While general relativity allows for the possibility of such space-time manipulation, it also presents enormous theoretical and technological challenges that must be overcome before the Alcubierre Drive can transition from a fascinating concept to a practical reality. Perhaps the most significant hurdle facing the realization of the Alcubierre Drive is the requirement for negative energy. This theoretical form of energy, unlike anything we have ever observed in the universe, is crucial for creating the space-time distortion necessary for the drive to function. Negative energy in this context would be responsible for expanding the space-time behind the spacecraft, effectively pushing it forward. The concept of negative energy is not entirely new to physics. It arises in certain interpretations of quantum mechanics, particularly in the context of the Casimir effect, where a small attractive force is observed between two uncharged conducting plates in a vacuum. However, the amount of negative energy required to create a warp bubble large enough for a spacecraft is staggering, far beyond anything we can currently generate or even detect. Some physicists speculate that negative energy might be found in exotic forms of matter or in the quantum vacuum, the lowest energy state of spacetime. However, these are still highly speculative areas of research, and the existence and properties of negative energy remain one of the biggest mysteries in modern physics. Even if we could harness negative energy, the technological challenges of building an Alcubierre Drive are immense. The amount of energy required to create a warp bubble, let alone sustain it for interstellar travel, would be astronomical, likely exceeding the total energy output of our Sun. Furthermore, the engineering challenges of manipulating space-time with such precision are beyond our current technological capabilities. We would need to develop entirely new forms of energy generation, storage, and manipulation. Material science would need to make unprecedented leaps to create a spacecraft capable of withstanding the immense stresses and strains of space-time distortion. And our understanding of quantum mechanics and general relativity would need to advance significantly to ensure the stability and control of the warp bubble. The Alcubierre Drive, though theoretically sound, remains firmly in the realm of science fiction for the foreseeable future. While the Alcubierre Drive offers a tantalizing vision of faster-than-light travel, it also presents potential dangers and paradoxes that must be addressed. One concern is the possibility of causality violations. If we could travel faster than light, it might be possible to violate the principle of cause and effect, leading to paradoxes such as traveling back in time and altering the past. The implications of such violations of causality are profound and could have unforeseen consequences for our understanding of the universe. Another potential risk is the accumulation of high-energy particles on the leading edge of the warp bubble. As the spacecraft travels through space, it would inevitably encounter interstellar dust and gas. These particles, when colliding with the warp bubble, could potentially release enormous amounts of energy, posing a significant threat to the safety of the spacecraft and its occupants. Additionally, the intense gravitational forces involved in warping space-time could have unpredictable effects on the spacecraft and its passengers, potentially leading to time dilation effects or even physiological harm. Despite the immense challenges and potential risks, the Alcubierre Drive continues to captivate the imagination of scientists and space enthusiasts alike. It represents a glimmer of hope, a tantalizing possibility that we might one day overcome the limitations of conventional space travel and venture out into the cosmos. While the Alcubierre Drive is unlikely to become a reality anytime soon, it serves as a powerful motivator for scientific exploration and technological innovation. The pursuit of faster-than-light travel, whether through the Alcubierre Drive or other theoretical concepts, will undoubtedly lead to groundbreaking discoveries in physics, engineering, and our understanding of the universe. The dream of reaching for the stars, once confined to the realm of science fiction, is slowly but surely entering the realm of scientific possibility. The Alcubierre Drive, though a formidable challenge, represents a beacon of hope, a testament to the boundless potential of human ingenuity and our enduring fascination with the cosmos.